Good evening and happy Monday. Been a while. And last we met, we looked at the derivative of exponential functions, logarithmic functions, and the trigonometric functions. And so that was last Monday evening, right? This evening we are going to finish up derivatives. So we're going to start by looking at rates of change. Right, so derivatives as rate of change. We will then look at implicit differentiation, and this allows us to look at the derivative of the inverse trigonometric functions, right? So I was able to derive those derivatives using implicit. And implicit differentiation also opens up a new technique of finding derivatives known as logarithmic differentiation. So logarithmic differentiation obviously will make it easier to differentiate complex products or complex quotient functions, so avoid product and quotient rules, messy ones. But it also allows us to differentiate functions of the form f of x to g of x, right? So a function raised to a function, right? Specifically a non-constant constant function raised to a non-constant function, right? Something like x to the x. So I'm going to have to shrink it. There we go. That should be good. Height in meters of a projectile shot vertically upward from a point 2 meters above ground level with initial velocity of 24.5 meters per second is given by the function h equals 2 plus 24.5 t minus 4.9 t squared after t seconds. And so this is known as free fall motion. We are ignoring, obviously, drag, air resistance. There's a few things we want to do, right? First, it asks us to find velocity after 2 seconds, and then after 4 seconds. We're asked to determine when the projectile reaches its maximum height. Asked what is this maximum height? Right, then we're asked to determine when it hits the ground and with what velocity is it going to hit the ground. Right, so that h is called the position function. And it's going to give us, in this case, a height off the ground, but it gives us the projectile's position at t seconds. Velocity function, usually represented with a v of t. Right, well, velocity is change in position with respect to time. Right? Whenever we hear the word change or rate of change, we should now immediately think of derivative. Okay. Since velocity is change in position with respect to time, v of t would be the derivative of h with respect to t. Another notation that you may see me use a lot is h dot. Right, so that dot simply means derivative with respect to time. Right, it's 24.5 minus 9.8 t, right? And that's the derivative of h. This now allows us to answer part A, right? Once v of 2 and v of 4. V of 2, 24.5 minus 19.6.
4.9.
4.9. But now 4.9 what? And so what would the units of velocity be?
Meters per second.
Meters per second. V of 4 would be 24.5 minus what? 39.2. Yeah, 39.2. Which would give us negative 14.7 meters per second. So what does that negative tell us? So remember, there is a difference between velocity and speed. Right? It's moving in the negative direction, which in this case is down. It's falling at that point. Right. Now, the beautiful thing about these types of problems is we can define our coordinate system however we want. Right. So if instead I wanted to say that down is the positive direction, I could easily do that. I'd have to multiply h by negative. then these signs would flip, right? This would be negative 4.9, and VF4 would be positive 14.7. All right. Now, when does it hit, or when does it reach maximum height? Okay, well, think of it. And of course, already it's going to be wonky. It says it starts 2 meters above the ground, right? So I'm going to do something like this. They're going to say that that represents ground level, y equals 0. It starts at a height of 2 meters. It'll go up before dropping back down. And obviously it's going to hit the ground. At that point is going to be its highest point, its maximum height, right? At that instant, what is its velocity?
Is it 0?
Right? At that instant, it has to be 0 meters per second. Right? Because that is the point at which it's going to switch from going up to down. Right? So at that exact instant, its velocity is switching from positive to negative, so it means it has to be 0. It has to cross through 0. So to determine when it reaches its maximum height, set v of t equal to 0 and solve. Right, 24.5 divided by 9.8. Two and a half seconds. Technology is not my friend. .5 seconds, right? So that is the answer for B. I'm just going to write it out as a sentence. So the projectile reaches its maximum height after 2.5 seconds. Part C is what is the maximum height? Well, that's just h of 2.5, isn't it? But 2 plus 24.5 times 2.5 plus 4.9 times 2.5 squared. Minus 4.9 times 2.5 squared. So it's 32.6. Zero. So 32.6 meters. When does it hit the ground? Now that's also straightforward, right? Height has to be 0. So set h of t equal to 0 and solve. Now, we could try and solve this by hand. Doing that, we'd need the quadratic equation, right? The quadratic formula. Oh, there should be a t there, shouldn't there? 24.5 t, yes. Should be negative 4.9. All right, negative b plus or minus the square root of b squared minus 4ac all over 2a. I don't know why I put 2 there. That should be 2 times negative 4.9. gives us negative 0.08 and 5.08. One of these does not make sense. The time of launch for the projectile would be t equals 0, right? So any time less than 0 represents time before our problem started. And general time is not negative. So we take 5.08. The projectile is going to hit the ground after 5.08 seconds. And finally, they wanted velocity. And then it hits the ground. Right, that's what, 24.5 minus 9.8 times the 5.08. Negative 25.28. Excuse me, which makes sense, right? We know that when it hits the ground, it's moving down. So the velocity should be negative. So it hits the ground with a velocity of negative 25.28 meters per second. Stone is dropped into a lake, creating a circular ripple that travels outward at a speed of 60 centimeters per second. Find the rate at which the area within the circle is increasing after 1, 3, and 5 seconds. We're told it's a circular ripple. What is the area of a circle?
Pi r squared.
Just pi times the square of the radius, right? Right now, we're also told that this ripple is traveling outward at a speed of 60 centimeters per second. That speed is a rate of change. All right, so if we look at it and go, let's say that's our ripple. Right, it's traveling outwards, 60 centimeters per second. Right, so that's in all directions. That specifically means, of course, that the radius is increasing. By 60 centimeters every second. That allows us to say that the radius is 60 t. Right? This allows us to write areas now as a function of time instead of a function of the radius. Area is 3600 pi t squared. Right? Rate at which the area is increasing. Rate means derivative. We're looking for A dot. Seven 200 pi t. We want 1, 3, and 5 seconds. After 1 second, 7,200 pi units. Square centimeters per second. After 3 seconds, be what, 21,600 pi, and again, square centimeters per second. And then after 5 seconds, 36,000 pi square centimeters per second, right? Now it's asking, what can we conclude? If we look at this, as time moves on, the area grows faster, right? So the rate at which the area grows is increasing as time progresses. Specifically, notice it is increasing linearly. Right? It's increasing in a linear fashion. The tank holds 5,000 gallons of water, which drains from the bottom of the tank in 40 minutes. Then Torricelli's law, I think that's how it's pronounced, gives the volume V of water remaining in the tank after T minutes as 5,000 times the quantity of 1 minus 1 over 40 T all squared. Obviously, domain for T is 0 to 40. We are asked to find the rate at which the water is draining from the tank after 5 minutes, 10 minutes, 20 minutes, and 40 minutes. Right, we need V dot. First, we have a constant multiple, a scalar multiple, right? It's going to be the scalar now times the derivative of the function. This is a general power function. 2 times the function. To the first power times the derivative now of the function. Negative 1/40th. Two over 40 is 1/20th. 5,000 divided by 20 is the same as 500 divided by 2, which is 250. As a note, that quantity is always non-negative in our domain, isn't it? Which means that this negative tells us that it's constantly draining, right? The amount is decreasing. That is important because look what it's asking us for. It's asking us for the rate at which it's draining. This makes the draining the positive direction. So I'm going to use this function instead. I'm going to say this is the function that represents rate of drain. Right? Notice all I did was multiply by -1. I got rid of the negative. In this case, since we're looking for rate of draining, a positive rate of change represents draining. If it wound up being a negative rate of change, right, it would mean that it's actually filling back up. We want 5, 10, 20, and finally 40. If we plug these in, oops, I don't want negative, sorry. $875 over 4 gallons per minute. All right, which is 218.75 gallons per minute. Now I want to note that these two would be acceptable only because it's over 4, right? So 0.75, 0.25, 0.50, right? They represent something over 4. In this case, 0.75 would be 3/4. That's an exact answer. After 10 minutes, what do we get? $375 halves, or 187.5 gallons per minute. After 20 minutes, we're at 125 gallons per minute. And then after 40 minutes, that shouldn't be hard to see that that's going to give you 0 gallons per minute. At what time is water flowing out the fastest? Let's scroll up here. So when does the water flow out the fastest?
When t equals
When t equals, I'm sorry, what?
5.
5? Is there anyone who disagrees? Okay. This is why this question was asked. I disagree. While it's true that 5 is the first one we calculated, does time start at 5? Time starts at 0. So we have flow rates before 5 minutes. What do you notice, right? The flow rate is decreasing as time moves on. Specifically, it's linear, right? It's the first power. The fastest flow rate is right when it starts at 0 minutes. Right? Word problems can be tricky. Then it asks, when is it flowing out the slowest? Well, that is obviously 40 minutes. Current exists whenever electric charges move and is the rate at which the charge flows through a surface. We're then given the quantity of charge Q in coulombs. Pretty sure that should actually be a capital C. That is passed through a point in a wire up to time t being measured in seconds. It's given by Q of t is t cubed minus 2t squared plus 6t plus 2. Asked to find the current at half a second and at 1 second. But then it's going to ask us, at what time is the current the lowest? Current. It's typically represented with a capital I. And it's the rate of change of charge. So it's Q dot. What are the units?
coulombs per second.
It would be the coulombs per second. Which is given a special name. The ampere, or simply the amp. Right, so we want current after half a second. And so it'll be 3/4. All right, since it's in decimals, we're going to keep it in decimals, so 0.75 minus 2 plus 6. Oh, I know why. 4.8. $4.75. $4.75 amps. Then at 1, just be 5 amps, wouldn't it? At what time is current the lowest? Right. So think back to when we studied the graph of quadratics. What is the leading term? Or more specifically, what is the leading coefficient? And what is the leading coefficient of I? It's 3, isn't it? Which is positive. Oops. Which tells us that this quadratic opens upward. So it's going to have a min at the vertex. In this case, we have a t coordinate, right? We have a t-axis and an I-axis. The t would be the x, the I would be the y. The min occurs because they're asking for what time it occurs, right? They don't care about what the minimum current actually is. They're just asking for when does it occur. So we're looking for the x coordinate only of the vertex. Negative b over 2 times a. And why did you just zoom out? That is not. Oh, lovely. Getting real sick of technology today. So the current is lowest after 2/3 of a second. Newton's law of gravitation says that the magnitude F of the force exerted by a body of mass little m on a body of mass big M, or vice versa, is given by G times little m times big M over little r squared, where G is the gravitational constant, it's the universal gravitational constant. R is the distance between the two bodies. First, we're asked to find dF dr and explain its meaning. So let's do that first. Well, G is a constant, right? It's the universal gravitational constant. M, little m and big M, mass. Is mass constant? I thought they did poles. They must have taken that out. Results. That should be good. All right, so let's see what we get. Do we think mass is constant? We only have 3 votes in so far. So far, it's overwhelmingly yes. And we have 6 votes in. So everyone who voted yes. Technically speaking, mass is not constant. Believe it or not, mass is actually a function of speed. So the faster you travel, the faster an object is traveling, the larger its mass. However, we are going to ignore relativistic effects here. And we're just going to assume that the masses are constant. Right? Because for very low speeds, the increase in mass is negligible. So we will take mass to be constant. This means there's only one variable in our function, and that's r. It's actually 2g little m big M over r cubed. Negative 2g little m big M all over r cubed is our derivative with respect to r. I'm going to explain its meaning. Right. It represents the rate at which the magnitude of our gravitational attraction is changing with respect to the distance between the two objects. Specifically, it is decreasing as the rate or as the distance between the objects increases, right? And it decreases proportionally to the inverse cube of their distance. Right? So what this is saying is the further apart the objects get, the less gravitational attraction there is between them. So now it's stated that let's suppose it is known that the Earth attracts an object with a force that decreases at the rate of 2 Newton per kilometer when r is 20,000 kilometers. How fast does this force change when r is 10,000 kilometers? All right. First, use what we know. All right, so dFdr when r is 20,000, we know that is 2. I'm sorry, we know it is -2, right? It's decreasing. That has to equal -2g little m big M all over 20,000 cubed. This means that 1 is equal to g little m big M over 20,000 cubed. Which gives us a constant of 20,000 cubed. Now when r is 10,000, we're going to get -2 times, now we just said that g little m big M is 20,000 cubed, and that has to be constant. Right, and then over the 10,000 cubed. Now, I'm not going to actually worry about the units of G little m big M. Well, that's nice. 20,000 over 10,000 is just 2. So 20,000 cubed over 10,000 cubed is just 2 cubed. We get negative 16 Newton per kilometer. This one's cool. Force acting on a body with mass m and velocity v is the rate of change of momentum, where momentum is the mass of the object times its velocity. If mass is constant, this reduces to Newton's second law, F equals ma, right, which everyone's familiar with. However, in the theory of relativity, mass of a particle is not constant, as I just explained. It actually varies with velocity. And the function is m naught over the square root of 1 minus v squared over c squared, where m naught is the mass of the particle at rest. All right, so it's rest mass, and c is the speed of light. We're going to use this fact to show that F is m naught a over the quantity of 1 minus v squared over c squared raised to the 3/2 power. Force is dp dt. Right, where P is m times v. But we're now told that m is not constant. M is rest mass m naught divided by the square root of 1 minus v squared over c squared. So momentum P is actually m naught times v over the quantity 1 minus v squared over c squared raised to the 1/2 power. Note that m naught is constant. Right. So when you think of an object's mass, it's m naught that we're looking at. Right. So if you're told an object has a mass of 1 kilogram, that means its rest mass is 1 kilogram. So we need to take the derivative with respect to time of this function here. So I can do quotient rule. Would that be the best bet? No, I think I'm going to write this as a product rule. Just to make it easier. Now remember, product rule. Second function. Times the derivative of the first function. Plus the first function times the derivative of the second. Right, now remember, v is a function of time, right? So that's why the derivative of v is dv dt. So for the second function, right, it's a general power, -1/2, times the function raised to the -3/2. Now times the derivative of the function, derivative of 0. I forgot something. Derivative of 0, derivative of 1 is 0. That should be times, oh my, I really messed that up. Times negative, right now the derivative of v squared over c squared, which would be 2v over c squared, times the derivative of v by chain rule. Let's factor out a 1 minus v squared over c squared to the -3/2. What we're left with is 1 minus v squared over c squared to the first power. But what is dv dt? So what is change in velocity with respect to time? Isn't it just acceleration? Negative times negative is positive. That's gone. Right, a half times 2 is 1. We have a v squared over c squared times a. Could have factored out that a sooner. Well, look, that's 0. You're left with m naught a over 1 minus v squared over c squared quantity to the 3/2 power, which is what we wanted. Any questions? Okay. So we'll take our break. We'll come back at 7:50, and we will look at implicit differentiation. So I'll see everyone at 7:50. And we're back. Finishing up this evening looking at implicit differentiation. All right, so a circle, right? It's not a function. But we're still interested in finding the slope of a circle at a specific point. This is where implicit differentiation would come in handy. So it's best if we just jump right into some problems. And I screwed that up. Hold on. Let's do that. All right, what we want to do is find dy dx for each of the following implicitly defined functions. So here's the procedure. First, you want to take d dx of both sides. Right, on the left-hand side in this case, we have a sum rule, so we can just distribute the differential through. Derivative of x to the fourth, 4x cubed. Derivative of y squared. This is general power rule. 2 times the function raised to the 2 minus 1, then times the derivative of the function. Right, and then obviously derivative of y is just dy dx. Second step. And so I think the text breaks this into 3 steps. They can all be combined into one step, which is just solve for dy dx algebraically. Right, the first thing to do in that case is to move all dy dx terms to one side, move all non-dy dx terms to the other side. Right, so in this case, We just subtract 4x cubed from both sides. Right. Next step is to then factor out the dy dx. Right. And then the final step would be to just divide. And that would be dy dx. Right. This process is much, much simpler in Calc 3 once you learn techniques of Calc 3. Right, but for now, it's going to be a lot of algebra. All right, here. Again, we want to do the same thing, right? First, take d dx of both sides. Go term by term. Derivative of x to the 2/5. Now derivative of y to the 2/5. And then finally derivative of 1. Right? Move all dy dx terms to one side, all non-dy dx terms to the other. There's only one term for dy dx, so no need to factor. You get negative quantity y over x to the 3/5 power. Right. Derivative cosine. Derivative of sine of y. And then derivative of 1. Right. Isolate dy dx terms. There's only a single dy dx term, so there's no need to factor. We just divide by what we're multiplying dy dx by. And we get sine of x divided by cosine of y. Now, this cannot be simplified, right? Because it's sine of x over cosine of y. You're not taking the trig of the same angle. So that cannot be simplified. So we just leave it like that. Right. Differentiate both sides. And ddx of both sides. X squared times e squared. Well, isn't e squared a constant? So its derivative would be 2e squared x. Derivative of 2 to the y. This is an exponential function. Right? So its derivative would be the function 2 to the y times natural log of the base times the derivative of the power. And then derivative of 5 is 0. Isolate the dy dx terms on one side. Again, there's only a single dy dx term, nothing to factor. So we're just going to divide by that 2 to the y log of 2. X squared times tangent of y is equal to 50. Take d dx of both sides. Right, d dx of x squared tangent of y. This is a product, isn't it? Second function times the derivative of the first function plus the first function times the derivative of the second function. So So the derivative of x squared times tangent of y would be 2x tangent of y plus x squared times secant squared of y times dy dx. That equals the d dx of 50, right, which is just 0. Isolate dy dx terms. There's, again, only one of them. Oops. Right, so x over x squared will obviously simplify, but what about tangent of y over secant squared of y? Be sine of y times cosine of y, wouldn't it? And 2 sine y cosine y is the same as sine of 2y. So we can write a derivative as negative sine of 2y all over x. Okay. Take d dx of both sides. If you look at the left-hand side, that would be a general power, right? Now I have to take the derivative of what's inside. And that has to equal the derivative of 2, which is 0. If you look at the original equation, wouldn't that imply that 3x squared plus 2y squared is equal to the fourth root of 2? Which means that term would be 2 to the 3/4, or the fourth root of 8. Which is constant, right? It's non-zero, so we can divide by it. Right, subtract 6x. Divide by 4y. We get negative 3x over 2y. Again, take d dx of both sides. For natural log, remember what it was. Take the derivative of what we're taking the log of. Right? Derivative of x squared would be 2x. Now, derivative of xy is a product rule. Second times derivative of the first plus first times derivative of the second. Now plus derivative of y squared, 2y dy dx. Just move that up a little bit. Then you divide by what we're taking the log of. And then derivative of 1 is just 0. Now again, if we look at the original equation, actually, it doesn't matter, right? In this case, it actually really doesn't matter what it is. But this x squared plus xy plus y squared is going to be e. So just the numerator will have to be 0 in this case. Right. Move all non-dy dx terms to one side. Move all dy dx terms to the other. Well, we already have everything on one side, right? Equals 0. So we're going to move the two non-dy dx terms over. Right? Factor dy dx out. And now divide by what dy dx is being multiplied by. Dy dx would be negative 2x plus y over x plus 2y. D dx both sides. Left-hand side. General power rule. Right-hand side. It's just a simple sum rule. I'm also going to factor out that 2 on the right-hand side. That allows me to divide by 2. Now we have a problem. We have to divide by that x squared plus y squared plus x. But notice that will be 0 whenever we're at the origin, right? There's technically another point, -1, 0, I believe. However, that cannot be in our quote-unquote domain, right? Because it wouldn't satisfy this equation. You'd get 0 equals 1, which is nonsense. Oopsies. So that's why I'm only excluding the origin. Write this as 2 separate fractions. This just makes it easier to move the dy dx terms to one side. And then subtract y dy dx over x squared plus y squared plus x from both sides. We are also going to subtract the quantity of 2x plus 1. And so minus 2x minus 1 from both sides. Multiply everything through. Do I want to do that now? I'm going to have to do it eventually. I'm going to do it now. I'm going to go ahead and multiply everything through by x squared plus y squared plus x. Factor out of dy dx. At the same time, let's try and simplify. Two x squared y plus 2y cubed plus 2xy minus y. That can't be simplified, bummer. Well, x minus x, that's going to simplify, so that's nice. That'd be negative 2x cubed minus 2xy squared. That's minus 2x squared minus an x squared is minus 3x squared. Then just minus y squared minus x. Too many minuses. I'm going to factor negative out from the right-hand side. At the same time, I'm dividing by this term, this 2x squared y plus 2y cubed plus 2xy minus y. And there's dy dx. Are there any questions so far? Okay. Let's look at logarithmic differentiation so that we can find the derivative of a non-constant function raised to a non-constant function. Right, so here's the procedure. And again, it's easier just to explain it as I do the problems than to write it out. First, take the natural log of both sides. Then use the laws of logarithms to simplify. Now we take the derivative, d dx, of both sides. All right, so remember, when you take the derivative of a log, it's the derivative of what's inside the log divided by what's inside the log. Looking at the right-hand side here, we have a quotient rule. All right. Denominator times derivative of the numerator. Minus numerator times derivative of the denominator over denominator squared. I just simplify it. I just multiplied numerator and denominator by the 1 plus x. Multiply both sides by that y. But remember what y was. 1 plus x to the 1 over x. I'm just going to do it this way, times. And this could be simplified. Okay, so we can write this as right, the denominator have the 1 plus x raised to the x minus 1 over all over x, right, using properties of exponents. And that's dy dx. Same procedure here. I'm just going to write it this way. I'm going to use y prime over y this time instead of dy dx. And so I'll just use y prime instead. Now we have product rule. So second function times the derivative of the first function plus first function times the derivative of the second. Right, so it's going to be y times that, right? But remember what we said y was. And then we can rewrite that. Let's write it in, do I want a quotient? No, I don't think I do. Let's write this as a product. And of course, if you really wanted to, you could also write it that way, but that doesn't matter. Any questions there? Okay. That leaves just one more thing to look at. Derivative of the inverse trigonometric functions. So derivative of the inverse sine of u is going to be u prime divided by square root of 1 minus u squared. Derivative of the inverse cosine of u. Negative u prime over the square root of 1 minus u squared. No, let's do tangent next. Derivative of the inverse tangent. U prime over 1 plus u squared. Derivative of the inverse cotangent. Negative u prime over 1 plus u squared. Derivative of the inverse secant. U prime over the absolute value of u times the square root of u squared minus 1. And then the derivative of the inverse cosecant. Negative u prime over the absolute value of u times the square root of u squared minus 1. All right, so the last few problems is going to be problems involving the inverse trig. Right, so what we want to do is find the derivative of each of the functions. H prime. So it's u prime, which is 2, over the square root of 1 minus u squared. Inverse secant. Derivative is u prime over the absolute value of u times the square root of u squared minus 1. Right? Well, remember with absolute values, if you take the absolute value of a product, it's the product of the absolute values. So we can write absolute value of 2t as 2 times the absolute value of t. Right? And so this simplifies to 1 over absolute value of t times the square root of 4t squared minus 1. Inverse tangent. U prime over 1 plus u squared. Right? This derivative is 2 over 1 plus 4x squared. Here we're working with a product. Second times the derivative of the first. Plus first times the derivative of the second, right? And that second function is inverse cosine. Right, negative u prime over the square root of 1 minus u squared. We now simplify this. And by simplify, just basically rewrite it. We get cosine of t times the inverse cosine of t minus sine of t over the square root 1 minus t squared. And here we have a quotient rule. Denominator times the derivative of the numerator minus numerator times derivative of the denominator all over denominator squared. Multiply numerator and denominator by square root of 1 minus x squared. And here's our derivative. Are there any questions on anything we've done tonight? All right, so if you take a look, so you have 2 assignments on Moderate Math that'll be due in 2 days, so August 2nd, 11:59 p.m. The report on an application of the derivative will be due tomorrow night. No, I'm sorry, I did make it due. Okay. So I did make that one due Wednesday night as well. Okay, perfect. So report on the application of derivative is also due Wednesday night, August 2nd. And you also have the second unit test. So the test on derivatives that will be due at the start of class on Wednesday. On Wednesday, we will be looking at our first applications of the derivative. Okay, so we're going to look at, come on. We're going to look at related rates. And we will then look at some approximations. So we'll look at differentials and how we can use that to approximate changes. We'll look at the linear approximation, which gives us a cool way of approximating certain values. So for instance, we can use a linearization to approximate the value of the square root of 2.1, for example. I'm sorry, 4.1. And then we also look at a method of approximating the roots of a function called Newton's method. Right. Newton's method is an iterative process, as we're going to see. All right. Which means it's kind of a pain to do it by hand. It's a lot easier to do it using technology. So I will break down how we can use Newton's method on a calculator, the TI Nspire, as well as a real simple code in Mathematica. So that is the goal for Wednesday. Everyone have a wonderful rest of your evening. See you all again Wednesday evening at 6 p.m.
Thank you.
Thank you.
Thank you.